Hi, I'm Roman Matzutt from Aachen University, and in the next couple of minutes I'm going to introduce you to CoinPrune, or how to securely prune Bitcoin's blockchain. For a motivation why we need block pruning, especially for Bitcoin, we first consider its ever-growing blockchain size. In 2019, Bitcoin's blockchain already exceeded a size of 250 gigabytes. Noteworthy, the blockchain contains all historic block data, which in the end is only really required to help new nodes, which join the Bitcoin network for the first time, to catch up with the latest state. In comparison to the blockchain itself, this state is only relatively tiny at sizes of around 5 gigabytes. Further, if we extrapolate Bitcoin's current blockchain growth, then by the time the 1 millionth block will be mined in 2027, the blockchain will have exceeded a size of 650 gigabytes. So we notice a strong and growing discrepancy between the size of Bitcoin's blockchain and the size of its state, which is required to operate the system. So we need to take action and restrict blockchain sizes before they become prohibitive. In our paper, we first conducted an extensive survey of approaches that either tackle the scalability of existing blockchain systems or that propose new blockchains with extended scalability in mind. While I'm not going into too much detail of this discussion here, I would like to refer you to our paper in case you want to get more information on that. Noteworthy here is that the approaches that aim to improve existing blockchains aren't really not that effective in the end. And on the other hand, novel designs are inherently incompatible with current blockchains and especially Bitcoin. So what we set out in our paper to do is create a secure and effective block pruning scheme for existing blockchains, especially keeping Bitcoin in mind as the blockchain that is currently already suffering from prohibitive blockchain sizes. So to understand our idea, first we have to recall that the blockchain in Bitcoin really is just a trust anchor. So as I already said, synchronization works by verifying the full history to ensure that all the information a joining node gets is correct, starting from a hard-coded Genesis block. However, this information becomes obsolete over time because transactions are spent and the new transactions are also spent, and so there is a lot of information in the blockchain that is not contributing to the current state anymore. But the current state is all I need in order to verify incoming transactions. So the state really is just a list or a set of unspent transaction outputs, and this is enough to verify future blocks, because I can, using this UTXO set, I can decide whether or not new transactions perform a double spending or not. And the idea of CoinPrune is to synchronize just via a recent state. The challenges here are to ensure the trustworthiness of the state wherever I obtain that from, and to ensure that our scheme remains compatible with Bitcoin. So to provide an overview of how CoinPrune tackles these challenges, let's consider the synchronization using standard Bitcoin, which, as I said, goes from a hard-coded Genesis block and obtains each block after the other and revalidates it and replace its contents to end up with the up-to-date UTXO set. What we seek to do is to derive a snapshot from all the old blockchain information in order to use that instead for bootstrapping, which means that we avoid sending all those blocks to joining nodes. And in the end, we also avoid having to store these blocks in the first place. So what we need to do here is to serialize the UTXO set based on a certain point in the blockchain verifiably, so that we can distribute this and keep up the trustworthiness of this snapshot. What we furthermore keep when synchronizing using CoinPrune is the header chain, because this provides proof that the latest blocks after the snapshot a joining node obtains contain valid proof of work from the genesis block all the way to the tip of the blockchain I'm synchronizing with. So then we are sure that no adversary is trying to build a false blockchain on top of the snapshot we obtain. And finally, what CoinPrune does is to download the full blocks after the snapshot for once, of course, in order to keep up with the current state. But what we also do is adding reaffirmations to these blocks, which are issued by CoinPrune supporting miners and state that the snapshot is correct that I obtained. And we can use this in order to decide whether we are synchronizing based on a correct snapshot or on a bogus one. So next up, for the snapshot derivation, what we do is we take the set of all unspent transaction outputs and split them into chunks so that we can distribute them independently from each other and enable parallel download from multiple peers to obtain a snapshot. Further, we add a snapshot header, which basically denotes the number of chunks that are in the snapshot and also ties the snapshot to a certain point in the blockchain so that we know to which point in the blockchain the state corresponds. To ensure the integrity of all chunks and the snapshot header, we derive an identifier for them individually based on Bitcoin's hash 256 function. And this allows us to detect wrong snapshot chunks. Because we finally derive a unique snapshot ID by concatenating all these IDs and hashing that again in order to derive the snapshot ID. And so if I'm getting bogus chunks, then the state I will derive won't match with the snapshot ID. So now that we know that how snapshots are derived, let's consider how we process reaffirmations of these states. What we do in CoinPrune is a pulse-based coordination. So considering this chain of blocks, CoinPrune supporting nodes just decide via hard-coded rules that a certain block in the blockchain is the first pulse block. And there is a pulse duration, which means after, let's say, 100 or 1000 blocks, there will be another pulse. And so all nodes know when each pulse begins. What we do now is we use the pulse block to derive the snapshots. So each snapshot is based on the UTXO set that was valid after one pulse block. What we further introduce is a reaffirmation window, which restricts the number of blocks after the pulse block in which we consider reaffirmations posted by CoinPrune supporting miners. So in this window we can either have reaffirmations of the correct snapshot, which is done by miners putting the correct snapshot ID into their blocks, or we can also have some malicious miners that try to reaffirm a false state that they want to distribute. So in order to keep the compatibility with Bitcoin, we cannot discard blocks containing false reaffirmations, but we have to outnumber them by honest ones. And then nodes or joining nodes can decide that even though there are wrong snapshot reaffirmations, they know which ones to discard. Furthermore, low adoption of CoinPrune amongst honest miners may lead to a situation where where malicious miners constitute a majority in posting bogus reaffirmations, but by restricting the reaffirmation window, we increase the hardness for them, or the required mining power they need in order to successfully reaffirm a state. So now a few words regarding the integration of CoinPrune with Bitcoin Core. So we have a proof of concept implementation available that we released as open source to GitHub, which is based on Bitcoin Core version 0.17.1. And in the future we also plan to release the states that we derived during our evaluation. So stay tuned for that. In order to post our reaffirmations into the blocks without losing compatibility to Bitcoin, we use the Coinbase field, which is one field in the Coinbase transaction that is only included into the block by the miner of the block. And fortunately, this is ignored by legacy nodes, so they don't care what's in this field, and so we can insert one reaffirmation per block per miner without losing compatibility here. And for receiving snapshots, we introduce an additional flag for supporting CoinPrune in the version handshake that nodes initially perform when they connect to each other. And we only require one new message type, which is the get state message, which is used to ask for the available states. And we introduce new state objects that are returned to such requests. Otherwise, we stay compatible with the current protocol. Some notes regarding the security of our system, especially regarding the synchronization process. So as I said earlier, the validity of the snapshots I obtain are paramount in order to keep CoinPrune secure. So our selection of the snapshot that I trust is based on the majority vote on the blockchain. So if I have a special trust in another party serving a state, maybe not via the blockchain but through other means like web servers and so forth, I can also put trust into them. But the fallback will clearly be that nodes synchronize via the Bitcoin network and then trust the majority of miners that successfully reaffirm a state or a snapshot. And because all the identifiers are known and interlinked, when I exchange a chunk, then the snapshot ID is also changed. I can easily detect when somebody tries to submit or to supply me with incorrect data. And I can avoid bootstrapping from a bogus snapshot. So regarding the reliability of our reaffirmations, so what we aim to do is a velvet fork, which really just means a fork that can be deployed gradually to Bitcoin without losing compatibility. But as I said earlier, this means that we need to tolerate invalid reaffirmations as well. So we really require an honest majority of CoinPrune miners to support our scheme. But we also think that this is feasible because of potential storage relief that they experience when many nodes are participating. And even if adoption remains low, our reaffirmation window protects us against one adversary with low mining power slowly but steadily reaffirming an invalid snapshot. Finally, briefly considering the peer-to-peer level, since we only introduce the get state message and don't alter the peer-to-peer protocol of Bitcoin whatsoever, we don't open up a new attack surface. And even if nodes think they are being betrayed via getting false snapshot information, there's a possibility to always restart and connect with new neighbors. So having that out of our system, let's consider what we actually gain using CoinPrune. So here we have the the storage requirements I showed on the first slide, this time in a logarithmic scale. And what we see here is that the blockchain, or that the storage requirements for Bitcoin nodes are strongly dominated by the raw block data. So by introducing our snapshots, as you can see here in the dashed black line, we really align well with the UTXO set. So because they are encoded differently than the UTXO set, our snapshots are sometimes a little bit larger, sometimes a little bit smaller than the UTXO set, but in general this aligns very well. And we also notice that the other components that we need to, in order to bootstrap using CoinPrune, are really of negligible size. So if we now compare Bitcoin Core and CoinPrune, we see that we are currently saving 2 orders of magnitude of storage requirements for all nodes, established nodes and joining nodes, which means also that traffic during synchronization is really going down due to CoinPrune's contribution. This also directly transfers to the synchronization times that joining nodes experience. So using a local testbed of a server that is being served the synchronization information by 8 commodity PCs with no additional latency added, we experience that Bitcoin Core still needs 5 hours to synchronize using our setup. In comparison to that, CoinPrune only needs 46 minutes to get up and running, which is also a vast saving for joining nodes. And oftentimes the synchronization time has been a major complaint by new Bitcoin users. So we really hope that we can help attract new users and also new devices to participate and become full nodes, which means that we have more redundant oversight over the Bitcoin blockchain and improve its security in the long term. To conclude this talk, we presented CoinPrune, which is a block pruning scheme for Bitcoin, which is realized as a velvet fork to be gradually deployable. And it relieves all nodes, established and joining nodes, from massive storage burdens, and also improves the synchronization times for joining nodes, which means that it's secure, efficient and fast. It's secure because miners reaffirm snapshot correctness. We can save up to 2 orders of magnitude in storage currently, and we reduce synchronization times from 5 hours to 46 minutes in our test setup. Finally, as I already said, our code is open source. It's available on GitHub. Feel free to experiment with that. And that's it from my side. I hope you have a good day. Goodbye.